hidden inside one of China's most advanced research centers. Scientists are pursuing a machine designed to recreate the power of the sun here on Earth. Every experiment begins long before the reactor starts, with hundreds of specialists preparing complex systems for another carefully controlled test. Every component must operate with extraordinary precision because even microscopic errors can interrupt the delicate balance required for nuclear fusion. Each reactor segment is manufactured to extremely tight tolerances before becoming part of the world's most sophisticated experimental fusion machine. Advanced machining transforms enormous steel forgings into perfectly shaped reactor components capable of surviving extreme operating conditions. Automated welding systems create exceptionally strong joints that will later withstand enormous mechanical and thermal stresses. Precision laser measurements verify every surface before each component advances to the next stage of construction. These superconducting magnets will eventually generate the invisible magnetic fields required to hold plasma without touching the reactor walls. Special insulation allows the magnets to operate at temperatures colder than outer space while carrying immense electrical currents. With each precisely positioned magnet, the artificial sun moves one step closer to becoming one of humanity's most ambitious scientific achievements. The vacuum vessel forms the heart of the reactor, creating an ultra-clean environment where fusion plasma can exist without contamination. Every connection is tightened to exact specifications, ensuring the massive structure remains perfectly sealed throughout future experiments. Thousands of sensors continuously monitor temperature, pressure, magnetic fields, and structural performance during every fusion experiment. Liquid helium cools the superconducting magnets to temperatures near absolute zero, allowing electricity to flow with almost no resistance. Specialized power systems supply enormous electrical currents required to generate the powerful magnetic fields surrounding the plasma. Autonomous inspection robots examine areas inaccessible to humans, verifying every internal surface before the reactor is sealed, before plasma can be created. Nearly every air molecule must be removed from the reactor to produce an ultra-high vacuum. Advanced control software analyzes millions of data points every second, helping engineers prepare for one of science's most demanding experiments. Years of engineering, manufacturing, and assembly come together inside a single machine designed to explore the future of clean energy. With every subsystem successfully verified, the artificial sun is finally ready for the moment scientists have been preparing for. After months of preparation, the reactor begins its carefully orchestrated startup sequence, where every operation must occur with perfect timing. Powerful vacuum systems remove nearly every remaining air molecule, creating one of the cleanest environments ever produced by humans. The superconducting magnets remain colder than outer space, allowing them to generate immense magnetic fields with remarkable efficiency. Invisible magnetic fields begin forming inside the reactor, preparing to suspend plasma without allowing it to touch the chamber walls. Only a tiny amount of hydrogen fuel is required, yet it will soon reach temperatures far beyond the core of the sun. Powerful heating systems inject tremendous energy into the hydrogen, transforming ordinary gas into an electrically charged plasma. Within moments, hydrogen transforms into a brilliant plasma, marking the birth of an artificial star inside the reactor. Because no material can survive these temperatures, magnetic fields alone safely contain the superheated plasma. Every millisecond, advanced diagnostics measure the behavior of plasma with extraordinary precision, ensuring the experiment remains stable. As temperatures exceed 150 million degrees Celsius, the reactor achieves conditions powerful enough to study the future of fusion energy. Powerful magnetic fields continuously adjust to stabilize the rotating plasma, keeping it suspended without ever touching the reactor walls. High-speed imaging systems reveal plasma behavior invisible to the human eye, allowing researchers to study every tiny instability. Thousands of measurements are collected every second, providing researchers with unprecedented insight into one of science's greatest engineering challenges. Sophisticated control systems make thousands of microscopic adjustments, preventing the plasma from becoming unstable during operation. Although the plasma reaches extraordinary temperatures, advanced cooling systems protect every critical component surrounding the reactor. Supercomputers compare live experimental measurements with advanced simulations, helping scientists better understand plasma behavior. Maintaining stable plasma for longer periods is one of the most important milestones on the path toward practical fusion energy. Each successful experiment builds upon years of previous research, steadily improving the performance of the artificial sun. Every stable second represents valuable scientific knowledge, bringing researchers closer to unlocking fusion as a future energy source. Inside this remarkable machine, scientists are proving that the dream of controlled fusion is no longer science fiction, but an achievable engineering reality. Sustaining high-temperature plasma for extended periods is one of fusion science's greatest engineering achievements. Every successful experiment expands scientific knowledge and improves the performance of future fusion systems. Thousands of sensors continue recording valuable information that will guide the next generation of fusion reactor designs. Fusion joins light atomic nuclei together, releasing extraordinary amounts of energy while producing no combustion and virtually no carbon emissions. Magnetic confinement allows scientists to safely control matter heated to temperatures far hotter than the center of the sun. The technologies being tested today could eventually become the foundation of tomorrow's clean electricity generation. Researchers around the world are working toward a future where fusion could provide reliable, large-scale, low-carbon energy. Although significant engineering challenges remain, fusion has the potential to transform how future civilizations generate electricity. Every completed experiment provides invaluable scientific data that brings practical fusion energy one step closer to reality. China's artificial sun stands as one of humanity's boldest scientific experiments, exploring a future where the power of the stars could one day fuel life on Earth. Fusion research never truly stops. Every experiment leads to new questions, new discoveries, and the next generation of engineering solutions. Every pulse of plasma generates valuable information, helping researchers refine future experiments with even greater precision. Advanced computing allows scientists to simulate conditions impossible to observe directly, accelerating the evolution of fusion technology. Fusion research extends far beyond a single laboratory, with scientists around the world contributing to a shared vision of clean energy. If fusion becomes commercially practical, future power plants could provide stable electricity with minimal environmental impact, although vastly different in size. The same fundamental process that powers our sun is being studied inside this remarkable machine. Every successful test is followed by meticulous inspection, ensuring the reactor is ready for the next scientific milestone. Behind every successful experiment lies decades of engineering, patience, and relentless scientific curiosity. This extraordinary facility represents more than advanced technology. It represents humanity's enduring pursuit of limitless clean energy. From a single ring of glowing plasma to the promise of powering future generations, the journey toward harnessing the energy of the stars has only just begun. Future fusion facilities may deliver continuous electricity to growing cities while reducing dependence on conventional energy sources. Reliable large-scale electricity could support advanced transportation systems operating around the clock with significantly lower emissions. Future industries requiring enormous amounts of electricity could benefit from dependable fusion-generated power operating day and night. Reliable electricity is essential for healthcare, scientific research, and critical infrastructure supporting millions of people. Abundant electricity could expand technologies such as seawater desalination, helping provide clean water to growing populations. The knowledge gained from fusion research may also influence future technologies extending beyond our own planet. Scientific progress advances through international collaboration, where shared knowledge accelerates discoveries benefiting researchers worldwide. Every completed experiment becomes the starting point for the next, steadily advancing the science of controlled fusion, built with extraordinary precision. The reactor stands as one of the world's most advanced experimental fusion systems. The quest to harness the power of the stars continues, driven by innovation, determination, and the pursuit of a cleaner energy future, even after the plasma disappears. The knowledge collected during each experiment continues shaping the future of fusion science. Every experiment adds another chapter to one of the largest scientific databases ever created for controlled nuclear fusion. Each generation of fusion technology builds upon the discoveries of the last, bringing scientists steadily closer to practical fusion power, while commercial fusion remains a future goal. Every successful experiment helps move that possibility closer to reality. The technologies developed today may inspire future generations of scientists and engineers to continue exploring the power of fusion. For now, the reactor rests quietly, waiting for the next experiment that could unlock even greater scientific discoveries. Behind these walls, researchers continue pushing the limits of science in pursuit of one of humanity's greatest energy ambitions. The same process that has powered the stars for billions of years is now being explored here on Earth through science and engineering. China's artificial sun represents decades of engineering excellence and the determination to explore a cleaner energy future. The journey toward unlimited clean energy is far from complete. But every experiment brings humanity one step closer. What began as an ambitious scientific vision has become one of the world's most advanced fusion research programs, bringing humanity closer to understanding the power of the stars. The same fusion process that has illuminated our universe for billions of years continues to inspire scientists searching for tomorrow's energy solutions, although many engineering challenges remain. Controlled fusion could one day reshape how future civilizations generate and use electricity. Behind every successful experiment are thousands of hours of engineering, precision manufacturing, and scientific perseverance. Our journey ends here, but the pursuit of fusion energy continues, driven by the timeless human desire to explore, discover, and innovate. From the first spark of plasma to the promise of limitless clean energy, the story of humanity's artificial sun has only just begun.